Hey, welcome back to Calculus. I hope you're doing great today. I'm doing great. We are going to talk about optimization in this video, and these are the kinds of problems that have lots of words in them, and that the problem is asking us to find an extreme value, so the maximum or minimum of some quantity. There's a number of problems in our book that look at building like areas that enclose animals, also known as pens, or just fenced-in areas. You could think of it like fencing in a yard. And so it's a relationship between perimeter and area is what is usually sort of leveraged in these problems, is that there's a relationship between perimeter and area, and we want to figure out what it is. So in this problem, we need to read with comprehension, and then we can start to mathematize some of the statements in our problem statement. So we have 400 feet of fencing to construct a rectangular fence for cattle. So we're going to build a rectangular fence that we're going to put some cows inside of. So that rectangular fence I've now drawn a picture for so that we have that visual representation which can help us set up equations and things like that. So the other thing that we might notice is that we're told fairly explicitly what is the quantity that we're trying to find the maximum or minimum of, and it's the area. So we want to maximize the area. So we probably will need to come up with an equation for the area, which means we might need to go label the side lengths of our rectangle so that we can understand the area as length times width. So we could do like a length on that side and the width on the other side. So our area is L times W, length times width, just like for every rectangle. And then the amount of fence we have is effectively the perimeter. So this idea that we have an amount of fencing, I connect that with the physical property of this picture as being the perimeter. So our perimeter is 2W plus 2L, and we need our perimeter to use all 400 feet. So if we have both of those things, now what we can do is take the perimeter equation, solve for L or W, and then plug this into our area equation. So this equation for the perimeter, whether it's this one, and really it's the one that has like the 400 in it, this is what's commonly known as a constraint equation. And the thing that we're trying to maximize is known as an objective equation. So the naming here is supposed to be helpful. We have a constraint on our problem. The constraint is we only have 400 feet of fencing. That's our limitation. We have an objective equation because our objective is to build a fence that has the largest area inside of it so that our cows have lots of room to roam around and eat grass and stuff. So the names are supposed to be helpful. All right, so now what we do, so let's do that process that I was writing that down there in orange. So let's take this 400 equals 2W plus 2L, and let's take our area equation and let's combine those together so that we can try to solve this with calculus. Because if we can get into one variable, then we can use derivatives and the first and second derivative test to find critical points and figure out which one gives us a maximum for the area. So if we work with this equation, 400 equals 2 times W plus L, I want to solve for one of the two variables, W or L. So I can factor out a 2 and then divide by that 2 and get 200 equals W plus L, which tells me that 200 minus L equals W. So there's manipulating that constraint equation so that one variable is equal to something involving the other variable. In this case, W equals 200 minus L. So then what we can do is take that and put it where W is. Doop. So we get that the area is equal to L times 200 minus L. And so our area equation is now 200L minus L squared. And so what we can do is use derivatives to find critical points and use our knowledge of something, whether it's the first derivative test, second derivative test, or the shape of this curve, to know if our critical point is a maximum or a minimum. So we can find dA dL, the derivative of A with respect to L, and we'll get 200 minus 2L. We can look for critical points. That derivative is defined everywhere. So our other critical point is when the derivative is equal to 0, that variety. And so we're going to look for when is 0 equal to 200 minus 2L. So we can add 2L to the other side and divide, and we get L equals 100. So add 2L to the other side and divide by 2. All right. So L is 100, which if we go back over here, boop, 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 that's going to tell us that 100 equals W, because 200 minus 100 equals 100. So we get 100 equals W, 100 equals L, which tells us that our maximum area is 100 times 100, which is probably 10,000 square units. And what were our units? I don't remember, so let's go back up. Feet. Okay, so square feet. Whoa. All right. So we've got our solution. The dimensions of our rectangle should be that the length and the width are equal, so we really want to build a square fenced-in area to maximize our area when we have a finite amount of fence to use. Our process of solving a optimization problem involves a lot of thinking before we start doing some calculus or any major arithmetic or algebra. We need to read our problem with understanding and understand everything that it's saying to us. We need to mathematize those ideas and create equations. In order to create equations, we have to invent variable names for the quantities that we are looking at in the problem, so that we can name those variables, we can create equations with them, we can have those equations interact with one another by taking one and solving for a variable and putting it inside the other, and then we can use calculus ideas to find a maximum of some curve or some function. The reason that we know this is a maximum I haven't yet addressed, but I'll address that right now quite quickly. This is a negative degree 2 polynomial. It looks like this, is its generic shape. So we know whatever critical point we find will be a maximum. So we can use the basic shape of a polynomial to help us know that we get a maximum when L is 100 and W is 100. So our maximum area is 10,000 square feet. I hope this video was helpful. Have a fantastic rest of your day.